This is Algebra 2 with Trig, 8C.1b. Today we're going to talk more about law of sines. We'll talk a little bit about law of cosines, and we'll discuss some more with the SSA case. We're going to start this off talking about area. Now, what we know about area of a triangle, you know area is half the base times the height. I didn't get that to fit there. Area equals half base times height. That's what you know about the area of a triangle. Well, what if we're given a measurement that we don't have a perpendicular set of sides? What if it's not a right triangle and we're not given that? Here we can use three different formulas. Let's zoom in here to explain where this is coming from. If this is angle A, this would be called side A. Angle B across from that is side B. Angle C across from that is side C. For us to figure out the area of this triangle, we need to know the base, so we're going to need to know B. And we would need to know the height of the triangle. But we don't know the height of the triangle. Make that H. We'll be under the impression that we know A. So if we're given A, then we can do sine of A, which would be the opposite over the hypotenuse. If you look here, by dropping down this dashed line, we're making an altitude. We're making 90 degrees with the opposite side. That is the height of the triangle. That's perpendicular straight up. It's called an altitude when it comes from your vertex. So opposite over hypotenuse, using your SOHCAHTOA that you've learned before, tells us that the sine of A is going to be the height over our hypotenuse. And the hypotenuse in this particular case is the letter C. For us to figure out what the height is, we're going to multiply the denominator to the other side. So we have C times the sine of A. That is our height. So if we bring it up to our formula here, and we say that our height is C sine of A, that's the height of the triangle. The base is still going to be, in this case, the base is the B. We have to take half of it, and that's the area. Area equals half B times C sine of A. We come over here, and we see that as our first option. The area equals half of B times C times the sine of A. If we're given a different angle, B, then we would turn it, we would have a height that would be different. A would be our value, C would be our value, and would be right here with AC times sine of B. So depending on what angle you're given, determines which of these three formulas. So I like to square off these three formulas because it gets a little confusing looking at them so tight together. These are three different formulas, and you choose any one of them that is going to work with the situation that you're given. So let's give this a try. You're setting up a triangular flower bed or flower garden in your backyard. If you lay off the lengths 15 and 11 with 62 degrees between the two sides, what is the area? So we're given 15 feet, we're given 11 feet, and 62 degrees in between. We don't even know what this side is. We don't particularly need it. We don't know what the height of the triangle is. but we don't particularly need it. We're going to use sine of 62 because that's the opposite over hypotenuse to help us determine what this opposite side is. So that's going to be considered our height. And then we have the base. So we take our base, which is 15, and sine of 62 times 11. So we often write it as 11 times the sine of 62. That's using the formula. I didn't particularly put letters next to it. We don't know which one we used, but it's always going to be in that pattern of here's our base. That was our height. Our height was calculated by the sine of 62 equals opposite over hypotenuse. You multiply the 11 to the sine of 62 to figure out the height. So this portion here is the height, and this portion here is the base. What did I miss on my formula? Times a half. So we pull this down and we say half of 15 times 11 times the sine of 62. Now you need to be sure you're in degree mode if you're going to use a degree value. And we get 72/84. And those would be feet squared, square feet. So over here for the next one, we're given our figure. Notice that in this situation we are given a side, an angle, and a side. Here we're also given a side, an angle, and a side. So that's telling us that this set of formulas is going to work for us, that we can use these formulas when we're given side, angle, side. Area of a triangle for side, angle, side. So the area equals half the one side, it really doesn't matter which one you choose first, times the other side, which is 1.4, times the sine of the angle. The order doesn't matter. It's all multiplication. 0.5 times 2.3 times 1.4 times the sine of 78.1, and we get, it's always surprisingly small here, 1.58. These are miles squared, or square miles. Questions about that? All right, so now we're going to talk more about both situations, law of sines, and we're going to lightly discuss law of cosines. We're not going to go into the formula, we're not going to do calculations yet, but law of cosines is a different format, a different set of formulas, a little bit more complicated, that we can use to solve when law of sines doesn't work. Now, we know that we can only use law of sines when we're given an angle and its corresponding opposite side. So if we know our angle here, we'll pretend that it's 20, and we have the corresponding side, we'll pretend that that's 11. Now we can have any other piece of information. It doesn't matter if we're given this one at 12, so we have side angle. If we're given 20, 11, and this angle, we'll call it at 110. That would be angle, angle, side. And I feel like we have another one in there that we can do also. This is the trickier one to identify, though. If you're given the 20 and we're given the 110, and instead of putting the 11 across from this one, we'll use this side. We'll just stick to what we've discussed earlier. We'll say that that's 12. This one is angle, side, angle. We can still use law of sines for this one. Why is law of sines going to work here? I thought to use law of sines you had to have the angle and its opposite side, at least for one of the pairs. I don't have the opposite side of 20, I don't have the opposite side of 110, and I don't know the angle opposite side 12.
Subtract 180.
You can calculate what that's going to be, and now you have that pair. So law of sines can work for angle, side, angle also. So that's why these are the three that you can use law of sines for. What you can't use law of sines for is if you're given three different side lengths. Let's just call it side A, B, and C. If we knew those numbers, we cannot use law of sines because I don't know the angle that's across from that particular side. We can't use trigonometry inverse to solve for it because it may not be a right triangle. So here we don't have the angle and its corresponding opposite side, so we cannot use law of sines. This would be side, side, side. And then the other one that we don't have it for, and to think there for a second, if we had two sides and one angle in the middle, we have the angle, but we don't have the opposite side, and we cannot use Pythagorean theorem to solve for the opposite side if it's not a right triangle. So we don't know this opposite side. Law of sines couldn't be used here. This is side, angle, side. So in these two cases, we're going to be using what's called law of cosines. We haven't learned about it yet, except we're just discussing it. Up here, we've learned about law of sines. And you would use law of sines to solve these three situations. So, let's give this a try. When given a non-right triangle, we cannot use triangle trick to solve it. We cannot use SOHCAHTOA. If you don't have a right triangle, a non-right triangle, we cannot use SOHCAHTOA. We can use law of sines when we're given it in a specific order, and in some situations we can use it to solve side angle side, or side side angle. That's what this one was. Angle side side, side side angle. This one was two angles and the non-included side, and this one was two angles and the included side. This is the one that required us to solve for that missing angle. Okay, we can use law of cosines. This is new. We can use law of cosines when we're given just three sides, or two sides and the included angle of the other one, just like we discussed down here. These are the two situations you use law of cosines, because you cannot complete the law of sines with the top and the bottom of one of the ratios. So let's look at these pictures and make a determination. Which method are they asking for here? It looks like they're giving us a side, they're giving us an angle in the middle, and a side on the outside. So this would be side, angle, side. Do we have an angle and its corresponding opposite side? We don't have it. We cannot solve for one of those missing angles because we can't subtract from 180 to solve for two angles. So this would have to be law of cosines. We don't know how to use law of cosines yet, but law of sines doesn't work there. So you need to know when law of sines doesn't work. This one, we have our angle and our two sides. Notice that the angle they give us, we have an S, we have an S, we have an A. Notice that the A is not in between the two S's. It's not side, angle, side, but it's two S's and the non-included angle. The angle on the outside of the sides. So we typically would write that SSA, and we'll label that as, we can use law of sines because I can connect my angle and the opposite side. We have one of the ratios for law of sines, so we can solve for any of the other parts. Here we have the angle and the opposite side. This is angle, angle, followed by a side. So AAS. So again, we can use law of sines because we have the angle and the opposite side. Here we have the angle and the opposite side. That's all I look for, regardless of the sides and angles. But I need an angle and its corresponding opposite side. We've got that. This one would be SSA, law of sines. This one, we have three sides, but we don't have an angle that would give us a pair that we can work with law of sines. So if we're thinking about law of sines, remember you can put the sides on top of the ratio, or you could put the sides on the bottom of the ratio, your choice. But for each one of these, regardless of which one it was, this would be our 3, this would be maybe our 9, this would be our 7. We don't have a complete fraction. We don't know any of the angles. We still have two unknowns when we're trying to cross multiply. You cannot use law of sines here. This is SSS. This would require law of cosines. Here's an angle and the opposite side, SSA. So we can use law of sines. Flipping this over, same idea. SSA, we can use law of sines. We have two angles, but the most important part is that I have an angle and its corresponding opposite side. Two angles and the non-included side. So AAS, we can use law of sines. SSA, we can use the law of sines. So the requirement is the opposite side and an angle. An angle and its corresponding opposite side. All right, any questions with that? All right, for this next situation, we're going to talk about a set of our notes that we had yesterday. Yesterday, if we back up a page, we had this chart. And we haven't gone into depth yet with this chart. We're trying to bring it in slowly. But this is for the situations that can happen under SSA. In geometry, we could not prove triangles congruent if the information was side-side angle. You can't prove triangles congruent using SSA because you have all these situations that might occur. One of the things, the A, it might be an obtuse angle, it might be an acute angle. So here's a situation you've got to watch out for. If it's obtuse, you might have a triangle and you might not have a triangle. We'll say that the angle they give us is A, just to make life easy. So if they give us A, side A, if it is too small, if it is so short that it is shorter than B, you're going to get no triangle out of that. So if A is less than B, it's going to be no triangles can be formed. Regardless of the angle, as long as it's obtuse, you would not have a triangle that's formed. There'll be no solutions, no triangle. Over here, if that A value is bigger than B and angle A is obtuse, then you're going to have one triangle that's formed. On this one, I guess I could even say equal. Less than or equal to. That would create no triangle. As long as it's greater than B, you can make one triangle out of it. The other situation we have is when the angle is acute. That's when it starts to get messy. When the angle is acute and that opposite side, angle A, is greater than B, then we're going to automatically be able to make one triangle. And it would have worked great last year if we would have had that information. But because we have this other situation, we just rule out this whole concept. So this is where A is greater than B. You're going to have one triangle because it's so long. I'll illustrate that. So one way to illustrate that, I'm going to place my angle right here on this line. So I'm not going to change the angle yet. Okay, there we go. Won't change it now. Here's my angle. I have this red side, I have this purple side, and I'm trying to get it to come down here and touch that line. So this would make a triangle, given angle, side, side. We would have to extend this side out, and then we would have a triangle. This is obviously acute. This looks now since I look at it, it does look more obtuse. Maybe in your video look, that might look close to 90 degrees. But we could have this triangle, and this angle out here would be acute for sure. Now what can happen is I can keep all the same information. I still have the same angle, the same red side, the same purple side, but I could swing over here and I have a totally different triangle. The area is dramatically different. The perimeter is different because this orange side would have to be shorter. This angle is now very obtuse. So we have two triangles made with this situation right there. And that's what we have to watch out for. When we drop down this height, this is the height that we are trying to determine. If this height is shorter than side A, and side A is shorter than B, then we're going to have two triangles. So if side A is greater than the height, but smaller than the red side, then we're going to have two triangles that are formed from it. If that side A is equal to the height, then we're going to have exactly one triangle that's formed. Something like that. And if that side A just happens to be too short, it's not longer than the height, it's never going to touch the ground. So this angle has to be smaller, or this A has to be longer. Something has to change. The numbers don't work. So there's a situation where A is less than the height. You're going to have no triangle formed. So that's an important set of information. This is how you read this chart. So now we're going to discuss it back here in those notes. All right, see if we can put this together. Caution needs to be exercised when using law of sines in SSA. It's called the ambiguous case. Depending on the relationship between the two sides and the angles, there could be no triangle, I illustrated that, one triangle, or there are possibly two triangles. If the angle is obtuse, thinking back to what I showed you with that, if the angle is obtuse, like this one here, and that opposite side is greater than the other side, kind of the adjacent to that angle, then we're going to have one triangle. If the side opposite the obtuse angle is smaller than the other side, how many triangles do we get? So if it's smaller than the other one, then there is no triangle. If the opposite side from the obtuse angle is longer than the other side, that was this situation, greater than the adjacent side, then there would be one triangle. If the triangle is acute, we need to be careful. That's this situation over here. We have more messes happening in this case. We have a situation where we're going to have one triangle if the opposite side is greater than the adjacent side. If the angle is acute, we need to be careful. If you ever get a domain error in the calculator, there are no triangles. That's kind of a quick way. You don't even need to know your numbers. You do some calculations, and if you get error, then you know that it doesn't exist. Because sine of theta is positive, using the unit circle, where is sine positive? In what quadrants? What is sine? Sine is the y value. And where in our xy axis is our r, the y value is positive? On the top. And the top, I know that's starting to look like cosine, but these are the two values where sine, the y values, are positive. What two quadrants are those? 1 and 2. This one is 3. This one is 4. So in quadrants 1 and 2, sine is positive. They're positive in both quadrant 1 and quadrant 2. So because sine is positive in both quadrant 1 and 2, we need to check if the supplement of theta can be used to form a triangle with. What that means, this is using kind of that trick. If we come over here and we find this angle over here, you can test it with the supplement because you form this isosceles an isosceles triangle. So this angle is the same as that one, which is supplementary here with the second triangle that we form. This would be supplementary to those. So if you get an error when that occurs, that means this angle doesn't exist. But if you can get a result, then you can actually put a triangle together. That's what it's telling us. That would be the supplement, would be 180 minus our theta. If we don't get an error, if no error, then we can form a second triangle. Looking back at examples 1 through 9, determine how many triangles are possible. Using the SSA case is the only ones that we have to determine this. So if we come back here, here is an SSA. How many triangles can be formed in this situation? So what we would need to do is we're going to try to calculate this angle right here. So we're going to use 32 over the sine of 52 equals 42 over this angle. Sine of, call it what you want, we'll call it B. And we're going to cross multiply, so the sine of B is going to equal 42 times the sine of 52 divided by 32, because we'll have to bring that back across. Let's see what we get. We have 42 times the sine of 52 divided by 32. That gives us a value that is 1.03. I know that sine cannot be greater than 1. So we got that sine to be greater than 1. What we're going to look at is this height. I'm pretty sure this height is going to be longer than the opposite side, so no triangle is going to be formed here. The opposite side is too small. So if we think about this right triangle as the sine of 52 equals the height over the hypotenuse, and we multiply 42 times the sine of 52, I'm pretty sure we're going to have a value that's greater than 32, which we did. We got 33. So that's telling us right there that there is no triangle. We had a sine that was greater than 1 in our normal law of sines, then no triangles can be formed. That was a good example to go through. So how many triangles can be formed in this situation? We have 40, we have 13, and we have 16. So if you do your 13 over the sine of 40 equals 16 over the sine of B, and we get a value that's greater than 1, then we're going to have no triangles are formed. So I cross multiply, and I'm going to do the sine of B equals 16 sine of 40 divided by 13. And I actually got a result. So I know one triangle can be formed. I can figure out what that angle is by doing sine inverse of my value. So the measurement of angle B is going to be 52.29. So that's what this angle here would be, 52.29. If I swung it inside and looked at my supplement, 180 minus 52.29, and I get 127. Are these two angles adding together to be greater than 180? No. This adds up to 167. So that means this angle exists and we have two triangles formed. Alright, we will definitely talk more about this, but those were the steps that we needed to take. Find this angle, figure out its supplement, and this still gave us room to figure out another angle. We're going to sketch a triangle. Angle A is 36. Side A side B. So we're given SSA. What we're trying to figure out is what's happening with this 5. I'm thinking this 5 isn't going to touch. That's what my thought is. So a couple ways you could think about it is trying to figure out what this height is using sine of 36 equals the height over the hypotenuse, using that right triangle, and figure out if this height is shorter than this side. If it's longer than that, then the 5's going to swing and never touch the ground. The other way to do it is just ignore it and do the law of sines. And you do the math. And we divide by 5. And we get 15 times the sine of 36. We divide that by 5. And we get 1.7633, or round it to 4. This is too big. Sine has to be less than 1. So no triangles formed. You could think back here to taking your 15 and timesing the sine of 36. And we have a length of 8. So if this is a length of 8, then a slanted 5 is never going to touch. This 5 would swing, swing, swing because the height is 8. So because we got 1.7, you can stop right there. No triangles formed.